The Constitution of India. Preamble. We, the people of India, having solemnly resolved to constitute India into a sovereign, socialist, secular, democratic republic and to secure to all its citizens justice, social, economic and political, liberty of thought, expression, belief, faith and worship, equality of status and of opportunity, and to promote among them all fraternity, assuring the dignity of the individual and the unity and integrity of the nation. In our Constituent Assembly, this 26th day of November 1949, do hereby adopt, enact and give to ourselves this Constitution.
Very happy morning, students. I hope you all are good in your house and you must have collected your answer scripts and you must be knowing the places where you have gone wrong, or it's a very good chance for you to rectify your mistakes, right? It has given you plenty of opportunities to know the question paper or the pattern how we need to write in the answer sheet. So, I hope children, when we take mistakes, make sure that it is good that we do it and we do not repeat it again, right? And the second important thing which I want to remind you is about your health. I want to make sure that you all are drinking plenty of water, because there are some days the weather changes that we may not feel thirsty. Forget whether we are thirsty or not, make sure that you drink water at frequent intervals. Okay, take a sip of water frequently so that you always hydrate your body, because when your body gets dehydrated, our mind doesn't work, and when our mind doesn't work, your body, you become sick, you don't feel to do anything. So, you make yourself active, get up early in the morning, and you all are sending me good morning messages and I am happy with that. Of course, there are some children who are a little bit lazy even right now. So, I will make sure that you also get up early, because I want you to do physical exercises to rejuvenate your body blood cells so that you keep yourself active for the whole day. Never you should feel that, oh my God, why I should do this. You should always think that, yes, let me do this. So, you should be having that spirit of doing your work on time. Okay. So, as we have completed our S block elements, we are slowly moving into our next topic, the chapter which is P block elements. We know P block elements also are called as representative elements and they belong to the right end of the periodic table. So, why it is a P block element is just because the last electron enters the P subshell. When the last electron is entering the P subshell, we name that element belonging to the P block. And we know P block has got 6 groups, right from 13, 14, 15, 16, 17 and 18. So, there are 6 groups in the P block. The main elements which head these groups are boron, carbon, nitrogen, oxygen, fluorine and neon. So, these are the 6 elements which head the other elements in the group. Next, we will be knowing the electronic configuration. We are actually have studied the electronic configuration right from our 10th standard, NS2, NP1 to 6. So, we have S subshell getting 2 electrons and in P subshell we know maximum 6 electrons can be accommodated. Except for helium, which is at the right extreme of the periodic table, except helium which has got a configuration of NS2, that is 1s2, other elements of the P block has a configuration NS2, NP 1 to 6. If you see the oxidation state in general, it increases across the period right from +3, +4, +5 and then it becomes -2, -1 and 0, which is the noble gas elements that belongs to the 18th group of the periodic table. We have metals, we have non-metals and metalloids. because metallic is just because the metallic character actually decreases when you go across the period. Slowly it start behaving as a non-metals, and there are some elements which have both metallic and non-metallic character, and we call them as metalloids. So, and these elements especially they have very high ionization energy because they are closer to the nucleus, and the screening is not that because of the d electrons, d subshell electrons. So, what happens, the ionization energy is actually very high. And what about electronegativity is also very high in p block elements, and we also know fluorine is the most electronegative element in the periodic table. Now, when I talk about non-metals, these non-metals just like our S block elements what we learnt in the previous lesson, S block elements used to donate electrons, they lose electrons to become cations. But what these non-metals do, they start accepting electrons, they gain electrons to become anions. So, when a non-metal combines with a metal, it forms an ionic compound. Example, I can say sodium chloride. Sodium is a metal, chlorine is a non-metal, the compound formed is a ionic compound. But when a non-metal combines with a non-metal, it becomes a covalent compound. You can take silicon and chlorine, silicon tetrachloride or carbon tetrachloride. Both non-metals when they combine together, sharing of electron takes place rather than transfer. So, it becomes a covalent compound. Now, non-metallic oxides, the oxides formed by the non-metals, they are acidic in nature. They are completely acidic. Sulfur dioxide is highly acidic. Now, the first members of the p block elements, they show variation from the rest of the members in the group. Just like what we learnt in S block elements about diagonal relationship with lithium and beryllium, similar to that we can see here the first members like boron, carbon, nitrogen, they show some sort of difference from the other members in the periodic table. So, these are the main properties that we are learning about the p block elements. Now, to be specific, now in this chapter we are learning about 13th and 14th group element, because in your higher class, that is in 12th standard, you will learn about 15, 16, 17 and 18. So, here group 13 is nothing but boron family, because boron is the first member of that particular group. So, you call them as a boron family. Now, boron is not that frequent in nature, but it is occurring as orthoboric acid, very commonly occurring as orthoboric acid. The common isotopes of boron are B10 and B11. Electronic configuration of 13th group is Ns2Np1, which is the outermost configuration. Now, atomic radii increases down the group, because when we move down the group, we know not only the electrons becomes more, also the number of shells increases. So, when the number of shells increases, distance between the nucleus and the outermost shell also increases. So, that is why I say atomic radii increases. Now, ionization energy is not that expected that it actually decrease down the group. It should decrease, but here it does not decrease down the group, because the sum of the ionization, the first, second and third ionization energy, if you add, it becomes very high, and because of that particular reason they show a difference in the chemical property, which we will be learning very soon. And when you see the electronegativity from boron to aluminium, it actually decreases, but right after aluminium like gallium and all, it starts increasing. So, these are the general things about boron family. Some physical properties are there, then we will learn about the chemical properties also, and there we will be learning about some important compounds of boron, and you will also have some videos which are quite interesting to know about the facts. Now, let us see the chemical properties of boron family. Physical properties, hardly 2-3 points are given in your textbook. Just in one paragraph you can just refer, children. Chemical properties, if you see, boron has a very small size, and some of the first 3 ionization energy is very high, as we just discussed in the previous topic. They are very high, so they do not tend to lose electrons, because ionization energy is a process where electron is removed to make it a cation. So, here since the ionization energy required is very high, they don't tend to lose electron and gain a +3 oxidation state. Instead, they form covalent compounds. The +1 oxidation state is actually very less for aluminium and it increases with the decrease in the group. In trivalent state, if you see in BCl3, when boron is forming a trihalide, only 6 electrons are present, 1, 2, 3, 4, 5, 6. So what happens? The electron, they become electron deficient and they behave as Lewis acids. So they immediately react with the base and form a tetrahedral structure. But the same thing does not happen with aluminium. AlCl3, quite stable than boron, try to form a dimer with a tetrahedral structure like this. Okay. Now that is the difference between boron and aluminium. Now if you see the reactivity with oxygen, aluminium and boron, amorphous boron especially, they can immediately react with oxygen to form their oxide and react with nitrogen to form their nitrides. And the oxides of boron are actually acidic, so they react with a base or they can react with an alkali to form a compound. And aluminium and gallium oxides are amphoteric in nature, that is they show both acidic and basic character, and indium and thallium oxides are completely basic in nature. Now the reactivity of oxygen or with nitrogen has given us a few idea how they react. Now we have two more reactivities, one is with water, the other one with halogens. Let us learn the reaction of boron family with acid alkalis and also with halogens. Now boron, as I told you earlier, it shows a different character from the rest of the members of the family. It do not undergo any reaction with acids and alkalis. Absolutely there is nothing reacting happening between those two compounds. But aluminium, it gets dissolved in mineral acid and forms aluminium ions and also liberates hydrogen gas, and similarly it also reacts with alkali to form a complex with the liberation of hydrogen gas. The same boron members, when they react with halogens, they try to form the trihalides. We know BCl3, AlCl3, which have been used as a Friedel-Crafts catalyst, right. Now we will be learning some of the important compounds of boron family. But before that, there is something that is important, is the anomalous behavior of boron. Lithium, beryllium were showing a difference in their character from other members of the family because of very few reasons, having a small size, no d electrons or no d subshells, I will say, that is they cannot extend their orbitals. The same are the reason for boron being very small in size and vacant d orbitals. They do not have electrons to extend their oxidation state. Boron becomes electron deficient and try to behave as a Lewis acid. They try to accept the base immediately, that is they try to accept a pair of electrons and then form a different tetrahedral structure. But aluminium and other members of the family are able to extend their structure because of the more increase of d electrons, and also that they can they can extend their covalency, that is more than 3 or 4, which is not possible with boron. And when we study about the important compounds, we have few important compounds of boron. The first compound is borax. You would have heard this name, very common, borax, white crystalline powder, right. This is a white crystalline solid which has a formula of Na2B4O7.10H2O, right. It has actually a tetranuclear units of hydroxyl, and this is just a temporary formula where we will be using this as a borax. This borax readily dissolves in water to form an alkaline solution, that is an alkali, which is sodium hydroxide. When you heat borax, it actually loses water molecules and try to swells up. Means whenever the water is lost, we have studied already, whenever the water is lost, the molecule actually swells up, and on further heating, it gets converted into a transparent liquid. Now that liquid gets solidified over a period of time and forms a glass like material, which we call it as a borax bead. I repeat children, when you heat borax, start losing water, it swells up, which on further heating gives a transparent liquid. That particular liquid gets solidified over a period of time, forms a glass like material which is borax bead. So this is a reaction where you can see borax on heating losing the water molecules, which again on further heating giving a glass like material, that is borax bead. Now this borax bead test is used to identify the metal, because most of the metal borates, they have their characteristic color. So when you do this borax bead test, if you get a particular color, you can identify that there is this metal present in that compound. So this test is very useful in finding the metal that is present in that particular compound. Next we will learn about orthoboric acid, diborane. There are some important compounds about boron. We have come to the next compound of boron, which is orthoboric acid, where you can see the formula H3BO3 or BOH thrice. Okay, where you can see it's a white crystalline solid, soapy to touch and sparingly soluble in water, and it is highly soluble when it is placed in a hot water. Now let us see how boric acid, orthoboric acid can be prepared. Now when you dissolve borax in a mineral acid, an aqueous solution of a mineral acid, you get sodium chloride getting precipitated and orthoboric acid formed. This orthoboric acid has a layer like structure where the BO3 is being connected to each other through the hydrogen bonds. This is a weak monobasic acid. Mono means single, and it acts as a Lewis acid because it accepts an electron from the hydroxyl ion. So you can see orthoboric acid when reacts with water gives a cation and anion respectively, and this orthoboric acid when it is heated gives a metaboric acid, which on heated gives a boric oxide. If you see the structure of boric acid even in your textbook, you can see boron having 3 oxygen and it is connected to the hydrogen bonds, again 3 hydrogen will be there, and again which is connected to another BO3. So these hydrogen bonds actually connect the boron and oxygen. So that is with orthoboric acid. The next compound is diborane, which is an important compound being colorless but highly toxic in nature, which can catch fire when it is exposed to air. Now diborane has a formula of B2H6, which can be prepared when BF3 reacts with lithium aluminium hydride, you get diborane. Now there are 2 important preparations other than this. One is a laboratory preparation where you can see sodium borohydride reacts with iodine to form diborane, or boron trifluoride reacts with sodium hydride to form diborane. So one is a laboratory preparation, the other one is an industrial preparation. So you can select whichever you want and feel comfortable. This diborane, when it reacts with air, it immediately catches up and it forms a boric oxide, and this is a highly exothermic reaction because it gives out a large amount of heat energy during the reaction. But when it is hydrolyzed with water, it forms BOH thrice, which is again a boric acid. So diborane when it is hydrolyzed gives boric acid. If you see the structure BH3 or B2H6, there is one, it is sp3 hybridized, but there is one orbital without an electron. So there are 2 hydrogens of each boron, which forms a bridge like bond between the 2 B compounds, that is boron element. So that bond is called as a banana bond, and that structure is important because they may ask you to draw the structure of B2H6 and try to explain the nature of hybridization in boron and also the type of bond that is formed between the 2 boron atoms. Now we have one more compound, that is we have almost completed all the compounds. Now we will be having the uses, which you can actually refer your textbook to study the uses of boron, aluminium. You know, aluminium ores are being used widely in the aircraft industry, right? So all those things you can just refer. Then we will get back into our 16th group family, which is carbon. Let us now learn about the structure of some compounds of boron. Boron has different structural compounds. It belongs to the 13th group of the periodic table. It has boron, aluminium, gallium, indium and thallium. Of all, boron is a rare element found in the Earth's crust. It is a black crystalline solid with an atomic number 5. Now this boron has some of its compounds which are borax, orthoboric acid and diborane. Let us now learn about each of these boron compounds one by one. When we are learning the compounds of boron, we need to learn the molecular formula and the structure. First compound is borax. Now, what is borax? The chemical formula is given there. It's a white crystalline solid which is soluble in water. It exists as an hydrate. If you see the structure of borax, you have BOOO-OH bond, which is a tetrahedral unit, and a BO2-OH bond, which is a trigonal unit. So it has two trigonal units and two tetrahedral units, which gives it a structure like tetrahedral geometry. Now each of this BO2 and BO3 structures is being adjusted by the OH bond which is attached to the boron. So you can see the structure of borax clearly, which is also given in your textbook. Next is orthoboric acid, which is again a white crystalline solid and that is soapy to touch. It is also known as boric acid. If you see the structure of orthoboric acid, it has B with connected to 3 of the oxygen atoms in a planar fashion. And this structure where you have hydrogen which is connected to 2 oxygen atoms forms a bridging bond between the BO3 structures. And thus it gives a trigonal planar layer structure for the boric acid. So here is the structure of boric acid. Now next, let us learn about diborane. Diborane is another structure of boron, which is again a compound which has a colorless toxic gas, which is formed with 2 boron and 6 hydrogen atoms, where the terminal 2 pairs of hydrogen are connected to the boron at each corner, and the pair of hydrogen which is connected to 2 boron occupies the center. The terminal hydrogen 4 hydrogen has a 2 center 2 electron bond, and the middle hydrogen, a pair of hydrogen, has a 3 center and a 2 electron bond, which is also called as a banana bond. Thus is the structure of diborane with B2H6. So let us quickly do a summary of borax, orthoboric acid and diborane.
We are getting into the 14th group elements, which are called as the carbon family members. If you see the electronic configuration, it is Ns2, Np2, 1 electron getting added again to the p subshell, being the 14th group member of the periodic table. And the carbon family is quite different because you can see metals, non-metals, metalloids, everything in the 14th group elements, widely used everywhere as silicon chips, right, and also for making our solar cells, right, from so many minute things. If you see the 14th group members, they play a very vital role. And if you see the atomic size gradually increases down the group, because as the same reason again, the number of shells actually increases. and here you don't speak about the ionic radii, you have a covalent radii. It's a mutual sharing of electrons, and the radius is more than that of the 13th group, but it's actually what happens as it is compared to the parent atom, there is a small difference. And if you see electronegativity, again there is a tendency to decrease when you go down the group in the same 14th member. The repeated oxidation state, which is most common in the 14th group, is +2 and +4, out of which the stability of +2 is actually varying when we go down the group, but +4 becomes more common, as we always say these are tetravalent in nature. When it reacts with oxygen, there are two types of oxides formed. One is MO type, where you can see carbon monoxide, and MO2, where you can see carbon dioxide, silicon dioxide, other examples. Some of the oxides are acidic in nature, some are neutral, that is neither acidic nor basic, and some are amphoteric, which shows both acidic and basic property. And if you see, when they are hydrolyzed in water, no carbon, silicon and germanium, they do not react with water. But what happens when tin combines with water, it forms tin oxide. The oxide of that metal is being produced. And if you see the reactivity with halogens, it forms two types, one is dihalides, the other one is tetrahalides. The reactivity of dihalides is not that to a greater extent, but tetrahalides react to a greater stability, and all the tetrahalides are completely hydrolyzable. So when they get hydrolyzed, let's see an example. If I take silicon tetrachloride, when it is going to undergo hydrolysis, it tries to accept a pair of electrons, and what happens? One of the hydrogen combines with chlorine, comes out as HCl, and OH comes and attack my silicon, that is the central atom, being positive in nature. So when it reacts with 3 water molecules, 3 HCl are being removed and all the chlorine are replaced by the hydroxyl group, which we call it as a silicic acid. So this is an important reaction where they may ask you how to prepare silicic acid from silicon tetrachloride, or in other way, what happens when silicon tetrachloride reacts with water. So this is just like our substitution reaction, where an atom or a group of atom are replaced by another atom and a group of atom. If you remember, children, we have learned that. So this type of reaction actually takes place in the tetrahalides of carbon family, where producing the acids of that particular element. Now, carbon has got an anomalous behavior, as I told you. Being the first member of the 14th group, it behaves something different from the other members of the family. The most possible reason is its small size, and only s and p orbitals are available. It cannot extend its oxidation state more than 4, as there are no d orbitals available. But carbon is the only element in that family which is capable of forming p-pi bonding, which is nothing but an extension of overlapping of the orbitals. This carbon can also form a carbon-carbon covalent bond, which we have already studied, the property of carbon element being catenation. But as we go down the group, the atomic size increases, the electronegativity decreases. This is the only reason for carbon to make its catenation property decreases. For carbon it increases, but when we go down the group, the elements which belong to the carbon family do not show the catenation property because of decrease in electronegativity. So carbon, being the first element in that particular group, shows a very high range of catenation property. That's why several hydrocarbons have been formed with the name of catenation, right? So let us now learn about, almost we have completed this. Now we will learn about the allotropes of carbon and some important carbon compounds. Let us learn some of the allotropes of carbon. 3 important allotropes of carbon are there. We have diamond, graphite and fullerene. Diamond, being the hardest substance, it's a crystalline form of carbon, which each carbon is tetrahedrally connected or bonded to another 4 carbon atoms. It is sp3 hybridized, forming a tetrahedral structure. In space, if it is seen, it looks in the form of a 3-dimensional structure. Now why it is the hardest substance on earth is just because it is not that easy to break the covalent bonds in the diamond structure. Now if you see the uses, they are used in the dye industry and also to make the filament of tungsten in all the light electrical equipments. Okay. Now after learning about diamond, something that we have already known is a graphite, where you can see in pencil lids. It has a layered structure and not the forces that we see here diamond, where there are strong forces of attraction. Here it is weak van der Waals forces, so it is very easy to break the bonds. It is being connected with a hexagonal ring with 6 carbon atoms, and these carbon-carbon bonds are forming a layer with sp2 hybridization, forming 3 sigma bond and 1 electron with a pi bond. The electrons in graphite structure, they are actually free to move. I mean, they are mobile, not like in diamond where they are closely packed and they are rigid that they don't move out of each other. Here they are free to move, so they can easily conduct electricity. Being soft and slippery, you can cleave one layer of graphite very easily. It is used as a dry lubricant where oil cannot be used in the industry. The third form of allotrope is the fullerene, where graphite, when it is heated in an electric arc in the presence of a noble gas like helium or argon, it gives fullerene. It's a purest form of carbon is just because it has a cage-like molecule where the carbon-carbon bonds are connected. And example, you can take C60 where 60 carbon atoms are connected to each other, and you call that particular form of carbon as Buckminster Fullerene. There are 60 vertices, means 60 points with single and double bonds which are made up alternatively in the Fullerene structure. If you see, it has a ball like structure like this given in your textbook, page number 327. All the 3 forms are given. You have diamond, graphite and fullerene. And if you see, the graphite is more stable in the thermodynamically when you see compared to other forms of allotrope forms of carbon, and carbon black is obtained. You know what is carbon black, right? It is obtained by burning hydrocarbons in a limited supply of air. Charcoal and coke are obtained by heating wood or coal respectively at very high temperature in the absence of air. So these are also, when I say charcoal, coke or carbon black, these are also different forms of carbon, right, which are obtained in different methods. Now we will be seeing the important compounds of carbon. Uses of carbon you can write in your own words. So many uses are there. In graphites it is used, carbon black is used, charcoal is used, right. There are different uses of carbon which is used in different applicants. Now we will get back into some important compounds of carbon, where we have carbon monoxide, carbon dioxide, and we have silicon dioxide and silicones. Just 4 more compounds. With that we are going to complete this chapter.
The allotropes of carbon. Carbon belongs to the 14th group of the periodic table, and it is a non-metal having various properties different from other members of its group. Carbon is the 17th most abundant element in the Earth's crust, and it has the highest number of allotropes. Out of the 8 allotropes found with carbon, there are 3 important allotropes which are the most main category of allotropes of carbon, and they are diamond, graphite and fullerene. The difference is because of they may be light or heavy, or they may be crystalline or amorphous, they may be hard or soft, and their reactivity will be different. The crystalline forms of carbon are diamond, graphite and fullerenes. Out of the amorphous forms we have coal, coke and soot, which is lamp black. Let us now focus on diamond, graphite and fullerenes, which are the main allotropes of carbon element. Diamond.
Diamond is a crystalline form of carbon, and we have already seen how diamond looks, with its hardest substance being the allotrope of carbon. It forms a tetrahedral shape with the crystal lattice having carbon at its four corners with sp2 hybridization with a bond angle of 190.5 degrees. Having a tetrahedral geometry, diamond has a crystal lattice with a tetrahedral shape. The bond length of carbon-carbon is 1.54 Armstrong. This structure got repeated, which has given rise to a big crystal lattice being the hardest allotrope of carbon. So thus looks the structure of diamond. Next comes graphite. Graphite is soft, has a layered structure, and this structure of graphite makes sure that they have been connected to each other with the van der Waals forces, and each carbon atom occupying the corners, forming a hexagonal rings with the distance of 340 picometer. And each hexagonal ring forms a layer which is planar in nature, and the bond length being 141.5 picometer. This graphite having a layer structure with carbon at its corner makes an sp2 hybridization with each carbon atom forming 3 sigma bonds. The fourth bond, which is a free electron in each carbon atom, forms a pi bond which is delocalized, that makes graphite a good conductor of electricity. Graphite is being used in electrodes and also in pencil lead. Because of its conductivity, it has a good form of use as electrodes in most of the electrolysis. Next is Fullerene. Buckminster Fullerene was discovered in 1985. It resembles a geodesic dome which is being discovered by architect Buckminster, which is a Bucky Fuller. Fullerene has carbon atoms which are connected to each other forming a very big structure, and which is prepared by heating graphite in an inert atmosphere where you use inert gases like helium, neon, argon, etc. Fullerene has a ring-like structure with C60 or C70 carbon atoms, which can be a 5-membered or a 6-membered ring connected to each other. This is the most perfect allotrope of carbon, being very soft and does not have any balls in between. So this is the purest form of carbon structure. The shape of C60 molecule resembles a Buckminster Fullerene, which is in the form of a soccer ball, having a ring with a 5-membered or a 6-membered in its whole structure. The carbon-carbon bond length of a single bond is 143.5 picometer, and the carbon-carbon double bond length is 138.5 picometer and 138.3 picometer. Thus, Fullerene is fused with a 5-membered and 6-membered rings with carbon-carbon single bond and carbon-carbon double bond. It contains 20 6-membered rings and 12 5-membered rings. A 6-membered ring is fused with a 6 or 5-membered rings, which is again interlocked with another 5-membered or 6-membered rings. The type of hybridization is sp2 with a bond angle of 120 degrees, where each carbon atom in Fillerin forms a 3 sigma bonds with other 3 carbon atoms. So the structure of Fullerene is explained with its hybridization and a bond angle. Buckminster Fullerene has a wide range of application where it is used in nanotubes made of carbon, which forms a very wide application in the industry. So all the 3 allotropes of carbon has a main role in the industry.
We are going to learn about some important compounds of carbon, where you can see carbon monoxide, where it is prepared by the direct oxidation of carbon with oxygen, where it forms carbon monoxide, and also by the dehydration of formic acid with concentrated sulfuric acid. So water is removed and you get carbon monoxide. This carbon monoxide can also be commercially prepared. When carbon is passed over water, you get carbon monoxide and hydrogen, which is a combination which we call it as water gas or synthesis gas, which we have learnt in hydrogen chapter, if you can recollect, children. Same carbon and oxygen, when it combines with nitrogen, when nitrogen gas is also passed over coke and oxygen, you get carbon monoxide and nitrogen. The combination we call it as a producer gas. Carbon monoxide is a colorless, powerful reducing agent, but it's a poisonous gas also. Now this carbon monoxide is highly useful to reduce the metal oxides and convert them into their metals, where it is used in lot many extraction. The best example is an iron extraction, which we have learnt last year, where hematite ore is treated with carbon monoxide, you get iron metal and carbon dioxide. Now this carbon dioxide, you know, can also be prepared by using calcium carbonate, where it decomposes to form calcium oxide and carbon dioxide. Now this carbon monoxide is a very good donor. It donates electrons to another atoms, metals. That's why it forms a lot of metal carbonyls. Like you can see iron, pentacarbonyl iron, like hexacarbonyl nickel, tetracarbonyl nickel, where there are these carbonyls acts as a donor atoms. This carbon monoxide, when it combines with hemoglobin in the blood, it's highly poisonous because it does not allow the RBC to produce oxygen. So what happens, it does not allow the passage of oxygen comfortably, thereby causing a very bad, even death rate can be happening if carbon monoxide mixes with the hemoglobin. That particular compound we call it as carboxyhemoglobin. The next compound which we are all familiar with is carbon dioxide. Carbon with 2 oxygen atoms, which is formed by the complete combustion of carbon with oxygen, which forms CO2, or methane, when it reacts with oxygen, also forms carbon dioxide and water. And you know the very good process where green plants use carbon dioxide in the process by using sunlight and chlorophyll, where carbon dioxide combines with water to form glucose or starch, where their oxygen is released to the atmosphere, where we all get benefited. So carbon dioxide is the main constituent in the photosynthesis process. Now what is greenhouse effect? Now when in atmosphere, when there is a burning of fuels, or when there is an increase in the content of fuel exhaust, those gases increase the amount of carbon dioxide level in the atmosphere. When there is an increase in the amount of carbon dioxide, that particular effect we call it as greenhouse effect. Now solid carbon dioxide, also referred as dry ice, comes in 1 mark question, is used as a refrigerant, that is for frozen food. It is the best refrigerant used in the refrigerators. Next, gaseous carbon dioxide is used in soft drinks, where once you open your soda bottle, you know you get bzzz, effervescence coming out, right? That's because of the presence of carbon dioxide. That's why it is used as a fire extinguisher. This carbon dioxide has a linear structure with 2 sp hybridized orbital, and so it has carbon with double bond and a double bond. So this structure being linear can form a resonance structure. What do you mean by resonance? There are 2-3 structures where you cannot say which is a perfect structure for it. All the 2-3 structures can be the same structure you can write for carbon dioxide.
Such canonical forms of structures we call it as resonance structure. So, carbon dioxide is capable of forming a resonance structure. Now, we are coming to the last part where we are going to learn about the silicon compounds. 4 compounds are there: silicon dioxide, silicates, silicones, and the last one is zeolite. The chemical properties of carbon. Carbon's family consists of carbon, a non-metallic element, and it has silicon, germanium, tin and lead, which comes under 14th group elements. With atomic number 6, carbon has 6 protons and 6 neutrons. The electronic configuration is 1s2, 2s2 and 2p2. So it needs 4 more electrons to complete its octet, thereby becoming a noble gas configuration. Carbon in its form of charcoal does not dissolve in water, neither in acid. Carbon tries to combine with oxygen, forming carbon dioxide. This carbon will undergo oxidation to yield carbon dioxide, forming a linear structure. Now, charcoal, when it is burnt in sufficient oxygen, produces carbon dioxide. The same charcoal, when it is burnt in incomplete combustion in the presence of oxygen, will give carbon monoxide, which has a carbon triple bond oxygen. When a steam is passed over charcoal, it forms carbon monoxide and hydrogen. Carbon not only combines with carbon forming a single bond, it can also combine with the carbon or other atoms yielding double bond, and also with carbon and other carbon atoms forming a triple bond. Example, butane. This carbon has a tendency to form a long chain structure, which is polyethylene, a polymer which is used in the synthetic industry. So this is the nature of carbon, a property which we call it as catenation. Just similar to carbon, we have oxygen, nitrogen, hydrogen, chlorine and bromine forming bonds with each other. Carbon 60, which is fullerene, is a form of carbon where it's also called as buckyball, where the carbon is surrounded by the carbon atoms forming a ring-like structure. Carbon combines with silicon with the same group of similar size, forming a covalent carbide, which is silicon carbide. Silicon dioxide, when it is heated at a temperature of 2300 Kelvin, combines with carbon and forms silicon carbide. Summary: carbon is a non-metallic tetravalent element with atomic number 6. Carbon will become oxidized when exposed to excess air and forms carbon dioxide, and in insufficient air forming carbon monoxide. Carbon can form long chains. The differences between carbon dioxide and silicon dioxide. Carbon dioxide is a gas at room temperature, while silicon dioxide is a solid. This difference is due to the difference in their structure of carbon dioxide and silicon dioxide. There are other differences also. Carbon dioxide forms a simple bond, a double bond between each of the oxygen atoms, where carbon dioxide forms a linear structure. Carbon has 2 electrons in its inner shell, 4 electrons in the second shell, while oxygen has 2 electrons in the inner shell and 6 electrons in the outer shell. Carbon needs 4 more electrons to become octet, which is being given by the oxygen atom. So, carbon shares the electrons with the oxygen atom forming a double bond with each of the oxygen atom. So that is the structure of carbon dioxide, which makes it to behave like a gas at room temperature. Now let us learn about the structure of silicon dioxide, where it has 2 electrons in a shell, 8 electrons in the second shell and 4 electrons in the outer shell. So this silicon needs 2 more electrons from each of the oxygen atom. So 4 electrons from 4 oxygen atom will be shared by the silicon, forming a covalent bond, which is a single bond with each of the 4 oxygen atoms, and each oxygen atom will be bonded again to a silicon atom. The silicon dioxide forms a giant covalent structure, which is a solid hard structure having a very high melting point. Carbon dioxide is a gas. Silicon dioxide is a hard melting point, solid. Carbon dioxide forms double bonds with oxygen, while silicon dioxide forms single bonds with oxygen. Thanks. Structure of silicones and silicates. Silicon belongs to the 14th group of the periodic table. It is the second most abundant element in the Earth's crust. It has a tetrahedral structure where each silicon atom is tetrahedrally surrounded by 4 other silicon atoms, forming a diamond-like structure. Now this silica exists in nature in the form of silica and silicates. It has important compounds like silicon dioxide, silicones and silicates. Let us now learn about silicones and silicates. Silicones. Silicones has a structure of R2SiO unit, where this unit is being repeated continuously as a chain. Now to represent this chain unit, we can write it as R2SiO to the power n, where it is a continuous chain structure. This R represents a methyl group or a benzyl group. This is the structure of silicon, where it has been surrounded by R2 and O. It is thermally stable and it is resistant to chemical. It can be used in oil, grease and rubber material. It is also used in the electrical insulator and also a moisture proof in the water for fabrics. Because of this biological impact, it is used in surgical instruments and cosmetology. Let us now learn about silicates. Silicates has a structure of SiO4-, where each silicon atom is tetrahedrally surrounded by 4 oxygen atoms. So it has a tetrahedral structure. It is the second abundant element in the Earth's crust, as we said. It is found as sand and quartz crystal, which mainly comprises of silica. It is used in the utmost important in technology because of the latest updates, and it is also used in detergents and cosmetics. This is a small summary about silica and silicates.
The next compound which we are going to learn is about silicon dioxide. 95% of our earth crust consists of silica. Silicon dioxide is commonly called as silica or quartz. All these are the varieties of silica that we have. It has a covalent structure with a 3-dimensional network where each silicon atom is being connected to 4 other oxygen in a tetrahedral fashion, and each oxygen is connected to 4 silicon atoms. So there is a tetrahedral bond formation where you can see a frame structure of silicon dioxide, how it is being connected to 2 oxygen atoms, and the bond enthalpy of silicon and oxygen is very high. That's why it does not react with any other compound, because to break that SiO is not that easy. Silicon dioxide do not react with an acid or any other metals or halogens,
but it reacts with a base and also with HF. With a base it try to form Na2SiO3 and with HF is try to form silicon tetrafluoride. So some of the uses of silicon dioxide you also know as like sand or glass, how it is being used in other purposes, and it was an important gang that has to be removed in the iron extraction. Then comes silicone. This is a new term that we are learning. It is an organosilicon polymers, because we know polymer has got a unit where you have two hyphens written in the bracket, where this is a repeating unit where it goes on getting added to the same compound again and again. Now this is a unit which gets repeated with an aryl or alkyl substituted silicon chloride. So you have an alkyl chloride which reacts with silicon in the presence of copper powder. You get dimethyl silicon dichloride, which on hydrolysis removes the chlorine and adds the OH molecule, just like we learned there, right? And here this repeated unit, instead of your textbook I have put it as N units of this particular unit. This is nothing but RSIO, R2SIO, where hydrogen comes out as water molecule which undergoes polymerization to form the silicone. So in your textbook it is given in a straight chain, or you can also write in this form. If you see the properties, highly thermally stability and dielectric strength is very high, that is why used in electrical properties, and it has a resistance to oxidation of chemicals. That is why silicones have been widely used in the industries where like lot of application with stability are required. If you see silicones in the next page of 330, they are used as sealant, greases, electrical insulators and waterproofing of fabrics. Because of this high dielectric strength, in electric appliances it is used as an insulator because does not allow the heat or electricity to pass through them. The next one is silicate. In silicate, children, you just have to know one important silicate is zeolite, where you have feldspar. The second line please underline it, and the unit which is SiO4, 4 minus, that is the unit which comes in silicate, that you need to learn, and also the structure which comes in 1 mark with a tetrahedral fashion of Si with 4 oxygen atoms which is being connected by the dot. So this you just learn, which is given in this page. You can see the structure which is given here, that is important. One is zeolite, which we just learned, you know, where we learned in the hardness of water. Do you remember, children? So zeolite, you just have to know where in hardness of water, permanent hardness of water, ion exchange method, that is the first important thing that we use as a chemical. And you know ZSM, it is used in petroleum industry. The first 1 mark question in your 11th standard, which has come very frequently. Now I will be putting the videos related to these compounds, because in the compounds when I explain it through the video, when I am giving explanation, it will be easy for you to understand what is that particular structure, how it is formed and how the bonds are made, what is the formula of that compound, what are the uses of that particular compound. So definitely I think videos are helpful to you. If the video size is not that much efficient to be fitted, I may send it to you through your broadcast also in separate groups, which may help you to learn better as compared to the theory, because when we see visuals, that stays in your mind forever, right, children? So with this, the P block elements is getting over. If you have any doubt along with the classes, please underline it or mark the areas where you have some doubts in understanding, and try to learn the textbook. Keep your pencil in hand when you watch the video, underline each important thing, read it again and again, make short notes when the video is being taken to you so that you understand better. Okay, thank you so much. Have a great day. Take care.